Okay, hello everyone. Welcome back. In this video, I'm going to talk about adding strong acids or strong bases to buffers and how we can go about predicting the pH. It turns out that this portion has a lot of similarities to what we were doing in the titration, so it will be a good review of that material. Okay, just a reminder, buffers are solutions that have both weak acids and conjugate base within similar concentration ranges. So the concentrations are within a factor of 10 of each other. And the resulting solution resists changes in pH when diluted or acids or bases are added to the solution. And we can calculate buffers and only buffer pHs based upon the Henderson-Hasselbalch equation. And remember that these concentrations are initial concentrations, which is what makes this an approximation, but a very good approximation. Okay, so I have 10 milliliters of a 0.01 molar acetate buffer, has a pH of 5.1. We want to find out what is the concentration of acetic acid and acetate ion in this buffer. And so this is similar to the problem that I did in the previous video, but it's a little bit backwards. I know that I have a buffer, so I'm going to start with the Henderson-Hasselbalch. So the pH equals the pKa plus the log of the acetate concentration divided by the acetic acid concentration. And I know that the pKa of acetic acid is 4.7. And so this has a pH of 5.1 equals 4.7 plus the log of the concentration of the acetate divided by the concentration of the acetic acid. And so now I also know that the total concentration of the buffer is equal to the concentration of the acetate plus the concentration of the acetic acid, and it is equal to 0.010 molar. And so this means that I have two equations with two unknowns, and so I can solve for, last time I solved for the concentration of the base, so this time I'm going to solve for the concentration of the acid. 0.010 minus the concentration of the acetate. And so I can plug this in, and so I get 5.1 equals 4.7 plus the log of the concentration of the acetate divided by 0.01 minus the concentration of the acetate. And if I solve this, I get that the concentration of the acetate in my buffer is equal to 0.00715 molar. I can plug this in up here, and I can get that my concentration of my acetic acid is equal to 0.00285 molar. Okay, if the algebra here is tricky for you, go back to the previous video, chapter 17-9, because I work through this algebra in detail in that video. The other thing that you can do is you can use Wolfram alpha. Remember, Let me actually spell it correctly. Remember us using this in the equilibrium experiment? You can use wolframalpha.com to be able to show you the steps for solving the algebra in this problem. I'm also willing to go over it more in office hours if you need. Okay, so this answers the question. It wants to know what's the concentration of the acetate and the acetic acid in this buffer. And that is what we found. Okay, so now that we know something about this buffer, we are going to take this buffer that we just solved, we're going to take 10 milliliters of this 0.01 molar acetate buffer with a pH of 5.1, and we're going to react it with 2 milliliters of 0.02 molar HCl. And so what we have going on is we are starting with a buffer solution. So we have our acetate buffer, which means that the acetate's in solution with acetic acid and hydroxide. And we have 7.15 times 10 to the minus 3 molar acetate, and we have 2.85 times 10 to the minus 3 molar acetic acid. And that's what we found on the previous slide. And so this is our buffer. And we're going to use 10 milliliters of this buffer. And so now we have to think about what happens when we add HCl to this buffer. And so HCl is a strong acid, which means that it will react with a base. And the base in this buffer is our acetate. And so we have a reaction happening, which is our acetate plus our HCl is going to form acetic acid plus chloride. And so when I add HCl, I'm going to shift the amounts of the acetate and the acetic acid because I'm going to use up some acetate and I'm going to make some acetic acid. And so this is a single arrow, and so we are going to have to do stoichiometry to be able to figure out what is in solution after we do this reaction. And so to do that, I have to have moles. And so if I find moles, I have 7.15 times 10 to the minus 5 moles of this guy. I have 4 times 10 to the minus 5 moles of HCl. I have 2.85 times 10 to the minus 5 moles of acetic acid. This is where I start initially, what I mix together. So that's the 2 milliliters of HCl. And that's the 10 milliliters of buffer. And so a reaction occurs. And in this case, we have a 1-to-1 ratio, so we know that our HCl is going to be our limiting reagent, leaving us with 3.15 times 10 to the minus 5 moles of acetate and 6.85 times 10 to the minus 5 moles of acetic acid. So now to find the pH, I'm going to need to I still have a buffer, right? I have weak base and conjugate acid, and so this means that I have a buffer. And so to find the pH, I am going to use the Henderson-Hasselbalch. And so that's the concentration of my base divided by the concentration of my acid. Okay, and so I want to find the pH. I know that the pKa of acetic acid is 4.7 because that's what we've been working with, plus the log of the concentration of the acetate. Oh, that's wrong formula. Divided by the concentration of the acetic acid. So now I have to be able to find these concentrations. And so I'm going to use the fact that I know that concentration is equal to moles divided by the volume. And so my moles for my acetate is 3.15 times 10 to the minus 5 moles. And my volume is 12 milliliters because I have 10 milliliters of buffer mixing with 2 milliliters of HCl. And so I have 0.012 liters. And so this concentration is 2.63 times 10 to the minus 3 molar. And now I'm going to do the same thing for the acetic acid. Equals 6.85 times 10 to the minus 5 moles divided by the 12 milliliters, which gives me 5.71 times 10 to the minus 3 molar. And so now I have the values that I need to plug into the Henderson-Hasselbalch. pH equals 4.7 plus the log of the concentration of my base is 2.63 times 10 to the minus 3 molar divided by 5.71 times 10 to the minus 3 molar. And so my pH is equal to 4.36. Now, when I started this, I had a pH of 5.1. So by adding acid, by adding HCl, my pH went down. And that's what we would expect, because when we add a strong acid, we get rid of the weak base and we make more of the conjugate acid. And therefore, we would expect that pH to decrease. Okay, so let's work this problem going the other direction. But turns out that I have a typo, and this should be 0.0050 molar NaOH. Okay, so to start off with, I have a buffer of acetate, and so that means that I have the weak base in solution with the conjugate acid. And this is the same buffer solution that we've been working with. And so I have 7.15 times 10 to the minus 3 molar of this guy. And I have 2.85 times 10 to the minus 3 molar of the acetic acid. And so now, when I add NaOH, this is a strong base, it is going to react with the acetic acid because the acetic acid is a weak acid. Okay, so I'm going to write out my reaction. So I have my weak acid plus my NaOH is going to form acetate plus I lost my sodium, so it's going to form sodium acetate plus water. And so this is a single arrow, and so this is stoichiometry, which uses moles. And so I'm starting with 2.85 times 10 to the minus 5 moles of this, of the acetic acid. I have 1 times 10 to the minus 5 moles of NaOH. And I'm starting with 7.15 times 10 to the minus 5 moles of sodium acetate. The NaOH is my limiting reagent. And so that leaves me with 1.85 times 10 to the minus 5 moles of acetic acid and 8.15 times 10 to the minus 5 moles of sodium acetate. I have weak acid and I have conjugate base in solution. That means I still have a buffer. And so to find the pH of this new solution, I use the Henderson-Hasselbalch. Log of the concentration of the conjugate base over the concentration of the weak acid. And so the pH is equal to 4.7 plus the log. And so to find these concentrations, I'm going to take my moles divided by my total volume, which is 0.012 liters, and I get 6.79 times 10 to the minus 3 molar for my acetate, and 1.54 times 10 to the minus 3 molar for my acetic acid. I solve this and I find that the pH equals 5.34. And to sanity check myself, I see that I started with a pH of 5.1. My pH has gone up with the addition of NaOH, which is a base, which is what I would expect to happen. Because when I add a base, it reacts with some of the weak acid, creating more weak base, and just shifting this pH instead of completely changing the pH. And so notice how buffers maintain their pH even whenever we're adding strong acids and bases to the solution. They maintain that pH because some of the weak can react, and it keeps us in that buffer zone, allowing that buffer to respond rather than the strong acid or base to dominate the pH of the solution. Okay, so this ends my videos for chapter 17. You now have all of the information, theoretically, that you need for reading the textbook for chapter 17, working chapter 17 homework problems, and practicing using the the laboratory assignments for both the titration and the buffer. Now, remember that the problems and the materials and the extra help that is posted on the CH231 World Class page, those are not collected. Those are just extra practice, so that you can see how these problems apply in multiple situations. The things that are due are the laboratory assignments for the titration and the buffer. The titration one is currently posted. The buffer one will be available on or before April 30th. So keep coming to office hours, keep asking me questions. I'm here to help. Email me if you need me. Keep reading the book, and you are doing great. Thank you.